The idea of waves without water is one of those conceptual shifts that feels small at first and then keeps expanding. It suggests that the universe is not just made of stuff, but of patterns that can exist independently of substance. Light is one of the clearest examples of this, and yet, even this understanding does not fully answer the question of what light is made of. Fields describe behavior, not composition. They tell us how light moves, not what it ultimately is. For a long time, the wave description of light felt like a triumph. It explained bending, spreading, interference, reflection, refraction, and the quiet elegance of optics. It fit neatly with the idea that light was an electromagnetic disturbance moving through space. Many scientists were content to stop there, but nature rarely allows a single story to remain complete for long. There were details that refused to settle, small inconsistencies at first, then stubborn contradictions that grew harder to ignore. These contradictions did not appear in sweeping cosmic observations or distant astronomical measurements. They appeared in controlled laboratory settings, in experiments that examined how light interacted with matter at very small scales. Places where intuition is often least reliable, and where reality tends to behave in ways that feel slightly unreasonable. One of the earliest and most unsettling clues came from studying how light transfers energy. If light were purely a wave, then increasing its intensity should increase the energy it delivers smoothly and continuously. Brighter light should always mean more energetic effects, but this was not what experiments showed. When light struck certain metals, it could eject electrons from their surface. This phenomenon, later called the photoelectric effect, behaved in a very particular way. Below a certain frequency, no electrons were ejected at all, no matter how intense the light was. You could flood the metal with low-frequency light and nothing would happen. Increase the frequency just enough, and suddenly electrons began to appear, immediately, even at low intensities. This was deeply confusing. According to wave theory, energy depended on amplitude, not frequency. Brighter light should have done the job regardless of color, but reality disagreed. Energy seemed to arrive in discrete chunks, tied to frequency, not smooth waves of accumulation. The implication was unsettling. Light did not deliver energy continuously. It delivered energy in packets. Each packet carried a specific amount of energy determined by the light's frequency. If that packet did not contain enough energy, no interaction occurred. This was not a small correction. It was a fundamental challenge to the idea of light as a purely spreading wave. Something else was going on. To explain this behavior, the concept of light particles returned, but not in the old simplistic sense of tiny glowing bullets. These particles, later called photons, were strange from the start. They did not behave like ordinary matter. They had no rest mass. They always moved at the same speed. They could not be subdivided. And yet, they behaved as discrete carriers of energy and momentum. Calling them particles was convenient, but misleading. Photons did not sit still. They did not occupy fixed positions. They did not follow definite paths in the way thrown objects do. They appeared when energy was emitted and vanished when energy was absorbed. Between those events, their behavior was best described by probability, not trajectory. Still, the particle idea explained something the wave picture could not. It explained why interactions happened in jumps rather than smears. It explained thresholds. It explained why light sometimes acted like a series of individual impacts instead of a continuous wash. At first, this dual description felt like a temporary compromise. Perhaps light was really a wave, but matter forced it to behave as if it were particle-like during interactions. Or perhaps light was really a particle, but many particles together produced wave-like patterns. Both explanations were attempted. Neither fully worked. What gradually became clear was that light did not fit into the classical categories at all. It was neither wave nor particle in the everyday sense. Those were metaphors borrowed from familiar experience, and light was politely ignoring their limitations. The idea that light consists of photons does not mean that photons are tiny objects flying through space like dust. A photon is better understood as a quantum of interaction. It is the smallest possible unit in which light can exchange energy with matter. When an atom emits light, it does not dribble energy outward continuously. An electron inside the atom shifts from one allowed energy state to another. The difference in energy between those states is released as a photon. That photon carries exactly that amount of energy, no more and no less. Likewise, when light is absorbed, an electron must absorb a whole photon at once. It cannot take half. It cannot borrow a little now and the rest later. The interaction is all or nothing. This discrete behavior is where the particle language earns its keep. It gives us a way to talk about these indivisible events. But it does not mean the photon is a tiny marble traveling along a track. Between emission and absorption, the photon does not have a well-defined position. Asking where it is at a given moment is often meaningless. What can be described is the probability of where it might be detected if an interaction occurred. This probabilistic spread behaves exactly like a wave. It diffracts, it interferes, it spreads out over space. The wave description tells us how the probability evolves. The particle description tells us what happens when probability collapses into an actual event. This is why light refuses to sit still. It cannot be pinned down to a single identity. It exists as a moving pattern of possibilities until an interaction forces a decision. Experiments that send individual photons through slits make this behavior impossible to ignore. Fire photons one at a time toward a barrier with two openings and detect where they land. Each photon arrives as a single point, a localized event, but after many photons an interference pattern emerges, identical to what a wave would produce. Each photon behaves as if it interferes with itself, not by splitting into smaller pieces, but by existing as a spread of possibilities until detection. There is no classical picture that makes this comfortable. It is simply how light behaves. The phrase particle begins to feel inadequate here. Particles, as we usually imagine them, have positions and velocities. Photons have momentum and energy, but position is a fuzzy concept until interaction. They are not objects moving through space so much as events unfolding in space-time. This becomes even stranger when considering that photons do not experience time. According to relativity, time slows down as speed increases. For something moving at the speed of light, time effectively stops. From the photon's perspective, if such a perspective can be defined, emission and absorption are the same instant. This means that while light may travel billions of years from a distant galaxy to your eye, the photon itself does not age. There is no journey. There is only connection. This property reinforces the idea that photons are not travelers in the usual sense. They are links between events. They connect changes in energy across space-time without themselves undergoing change. Calling this a particle stretches the word beyond its original meaning. But abandoning the word entirely would make communication difficult, so it remains, with the understanding that it carries caveats. Light's refusal to sit still also shows up in how photons behave in groups. They can bunch together or spread out depending on conditions. They can be entangled, meaning the behavior of one becomes linked to another even across large distances. They can interfere collectively or behave independently. These behaviors are not properties of classical particles. They belong to quantum entities, where individuality and separateness are not as clear-cut as intuition expects. Another sign that photons are not ordinary particles is their inability to exist at rest. You cannot trap a photon and hold it still. You can confine light between mirrors, bounce it around, slow it down in certain materials, but the photon itself always moves at the same fundamental speed. What changes is how often it interacts. This distinguishes light sharply from matter. Matter can be stationary. It can pile up. It can form structures that persist. Light does not settle. It does not accumulate in the same way. It is always in motion or gone. Yet despite this restlessness, photons obey strict conservation laws. Energy is conserved. Momentum is conserved. Interactions balance precisely. There is no fuzziness in the accounting, only in the paths between accounts. This blend of precision and uncertainty is characteristic of quantum behavior. Light was one of the first places where this behavior became undeniable. It forced a reconsideration of what it means for something to be made of something. If light is made of photons and photons are not material objects, then made of must mean something different. It cannot mean composed of smaller pieces in the traditional sense. It must mean structured by rules that allow discrete interactions. Light in this view is made of allowable actions, emissions, absorptions, transfers of energy and momentum that occur only in specific units. The photon is the name we give to one such unit. This perspective dissolves the conflict between waves and particles. The wave describes how the possibility of interaction spreads. The particle describes the interaction itself. Both are necessary. Neither is sufficient alone. As you rest with this idea, it may feel less like an answer and more like a reframing. The question shifts from what is light made of to how does light behave when it exists? Composition gives way to process. Light does not sit still because it cannot. It is defined by motion, by connection, by transfer. Even when confined, it is restless, bouncing, interacting, waiting for absorption. This restlessness is not chaos. It is structured, predictable, governed by laws that are astonishingly precise. The unpredictability lies not in outcomes as a whole, but in individual events. By the time scientists were forced to accept that light behaved both like a wave and like a particle, there was a growing sense that something deeper was being uncovered, something that did not fit into the old boxes at all. The problem was no longer deciding which description was correct. The problem was understanding how both could be true at the same time without cancelling each other out. Light was not politely choosing one role depending on circumstances. It was following rules that made both descriptions incomplete on their own. This is where the idea of a compromise enters, though compromise may not be quite the right word. It suggests negotiation, a middle ground, a blending of two familiar things. What light actually revealed was not a midpoint between waves and particles, but a framework in which those concepts were no longer fundamental. They became tools, useful in certain situations, misleading in others. To see why this was necessary, it helps to look carefully at what waves and particles represent in everyday thinking. A wave, in the classical sense, is extended. It occupies space. It spreads out. It can overlap with other waves and interfere. A particle, by contrast, is localized. It exists at a specific place at a specific time. It collides. It transfers energy in discrete impacts. Light stubbornly displays both sets of behaviors, but never all at once in a way that satisfies classical intuition. When light is traveling freely, spreading out from a source, bending through openings, forming interference patterns, the wave description works beautifully. When light interacts with matter, knocking electrons loose, triggering chemical reactions, or registering as a single detection on a sensor, the particle description becomes unavoidable. Early attempts to reconcile this often tried to keep one description primary and treat the other as an illusion. Some argued that light was really a wave, and particles were just artifacts of how matter responded. Others argued the opposite, that light was really made of particles, and waves emerged statistically when many particles were involved. Neither approach held up under scrutiny. Single photons produced interference patterns. Individual detection events obeyed wave-based probability distributions. The behavior did not depend on large numbers smoothing things out. It was intrinsic. This forced a conceptual shift that went far beyond light. It required rethinking what physical descriptions are meant to do. Instead of picturing what light is, physicists began focusing on what light allows to happen, and how likely different outcomes are. In this new framework, the wave is not a physical ripple moving through space. It is a mathematical object that encodes probabilities. It tells you where light might interact if it does. It evolves smoothly, spreading and interfering according to precise rules, but it does not represent something directly observable. The particle, on the other hand, represents the observable event itself. A click in a detector, a spot on a screen, an electron ejected from a surface. These events are localized and discrete. They are what you actually measure. The strange compromise is that both descriptions are necessary, but they apply to different aspects of the same phenomenon. The wave governs potential. The particle marks actuality. This is not merely a semantic distinction. It changes how experiments are designed and interpreted. If you set up an experiment to observe interference, you must allow the wave aspect to remain intact. If you try to track which path a photon takes, the interference disappears. The act of measurement itself determines which description becomes relevant. This is often summarized somewhat misleadingly by saying that light chooses to behave like a wave or a particle depending on how you look at it. That phrasing gives too much agency to light and too little to the experimental setup. Light does not choose. The rules governing probabilities and interactions simply play out within the constraints you impose. If you design an experiment that preserves information about multiple paths, the wave description applies. If you design one that forces a definite path, the particle description dominates. You cannot have both simultaneously in full form. This is not because light is hiding information out of spite. It is because the concepts of wave and particle are mutually exclusive ways of organizing information. They are not properties of light itself. They are properties of our descriptions. At first, this feels unsatisfying. It can sound like a retreat, as if science is admitting defeat. But in practice, it is the opposite. By letting go of the demand for a single classical picture, physicists gained a framework that worked consistently and predictively. This framework is quantum mechanics, and within it, light occupies a special but not unique role. Other entities, like electrons, also exhibit wave-particle duality. Light was simply the first place where the conflict became impossible to ignore. In quantum mechanics, the fundamental object is not a wave or a particle, but a quantum state. This state contains all the information that can be known about the system. It evolves according to strict rules, and from it, probabilities of different outcomes can be calculated. For light, the quantum state describes how the electromagnetic field is configured. It tells you the likelihood of detecting photons in various places, with various energies and properties. It does not tell you what will happen in a specific trial. It tells you what can happen and how likely each possibility is. When an interaction occurs, such as a photon being absorbed, one of those possibilities becomes real. The rest vanish from relevance. This transition from possibility to outcome is often called collapse, though that word brings its own complications. What matters here is that the wave description governs the build-up of possibilities, while the particle description governs the outcome. The compromise, then, is not a blend but a division of labour. Waves handle evolution, particles handle events. This division helps explain why light sometimes seems ghostly and spread out, and sometimes sharply localized. Between interactions, light is not an object in space. It is a pattern of probabilities. At the moment of interaction, it produces an object-like effect. This also explains why asking what is light really often leads to frustration. The answer depends on what aspect you are focusing on. If you mean how light moves and spreads, it is best described by waves. If you mean how light exchanges energy with matter, it is best described by particles. If you insist on a single picture that covers both perfectly, you will be disappointed. The compromise becomes even stranger when you consider that the wave description does not live in ordinary space in the way classical waves do. It lives in an abstract mathematical space that encodes all possible configurations. This makes it harder to visualize, but also more powerful. In this sense, light is not made of waves or particles. It is made of quantum states that produce wave-like probabilities and particle-like events. That may sound like wordplay, but it reflects a genuine shift in how physical reality is described. What is particularly striking is how precise this framework is. Despite its abstract nature, it produces predictions that match experiments to extraordinary accuracy. The rules governing light's behavior have been tested again and again, and they hold. This precision suggests that the compromise is not a flaw or a temporary patch. It is a reflection of how nature actually works at small scales. Our discomfort arises not because the theory is sloppy, but because our intuition is tuned to a different domain. Light does not care whether we find its behavior aesthetically pleasing or conceptually tidy. It behaves according to rules that are consistent, even if they do not align with everyday expectations. As you sit with this, it may help to notice that similar compromises appear elsewhere in life. A map is not the territory, but it is useful. A musical score is not the sound, but it guides performance. A recipe is not the meal, but it produces one. Different descriptions serve different purposes. Wave and particle descriptions are like that. They are not competing claims about what light is made of. They are complementary ways of organizing information about how light behaves under different conditions. The word complementary is important here. It does not mean redundant. It means mutually necessary and mutually exclusive. You need both, but you cannot apply both fully at the same time. This idea takes some getting used to. It challenges the expectation that a complete description must be singular and unified at all levels. Instead, completeness emerges from knowing when to use which description. Light embodies this lesson vividly. It forces a kind of intellectual flexibility, a willingness to let go of rigid categories and accept that reality may not fit neatly into them. This flexibility does not mean anything goes. The rules are strict. The mathematics is unforgiving. Predictions are precise. What changes is not rigor, but interpretation. As this part settles into place, the strange compromise between wave and thing remains active. unresolved in the sense that it does not collapse into something simpler. It remains a feature, not a bug. When the word photon is used, it often sounds reassuringly concrete, as if it finally gives light a smallest piece, something definite you can point to and say, this is it. This is what light is made of. A photon sounds like a tiny object, a grain, a bead of brightness moving through space. That image is understandable, but it quietly smuggles in assumptions that do not quite hold. Photons are messengers, yes, but they are not messengers in the way envelopes or packages are. They do not carry a note written on paper. They are the note, the delivery, and the act of delivery all at once. To understand why photons are described this way, it helps to return to the idea of light as interaction rather than substance. A photon does not exist as a thing sitting somewhere waiting to be picked up. It exists as a transfer. Energy leaves one place and appears in another, and the photon is the name we give to that indivisible transaction. Without an emission and without an absorption, the concept of a photon loses its meaning. This is one of the reasons photons feel so elusive. Most objects can be described independently of what they do. A rock is still a rock even if nothing touches it. A chair remains a chair whether or not someone sits in it. A photon, by contrast, is defined by what happens. It is born in an interaction and ends in an interaction. In between, it is described not as a location, but as a set of possibilities. When an atom emits light, it does so because one of its electrons changes energy levels. Electrons in atoms are not free to take on any energy they like. They occupy specific allowed states, like rungs on a ladder. When an electron drops from a higher rung to a lower one, the energy difference has to go somewhere. That energy is released as a photon. The photon's energy is exactly equal to the difference between those two states. It cannot be adjusted. It cannot be shaved down or stretched out. This precision is one of the defining features of photons. They are not vague carriers of some energy. They carry a specific amount determined by frequency. That frequency also determines the photon's character in other ways. Higher frequency photons carry more energy. Lower frequency photons carry less. This is why different kinds of light have different effects. A photon in the visible range might trigger a response in your eye. A lower frequency photon might contribute to warmth. A much higher frequency photon can break chemical bonds or damage cells. Despite these differences, all photons share some remarkable properties. They all move at the same speed in a vacuum. They all have zero rest mass. They all carry momentum even though they have no mass in the usual sense, and none of them can exist at rest. This last point is particularly important. You cannot stop a photon and examine it. You cannot put it on a scale. You cannot hold it still. The moment a photon stops moving, it stops being a photon. It has been absorbed. This makes photons fundamentally different from particles of matter. Matter can accumulate. Photons cannot. Matter can sit quietly. Photons cannot. Matter persists through time. Photons, in a sense, do not experience time at all. According to relativity, time passes more slowly for objects that move faster. As an object's speed approaches the speed of light, time dilation becomes extreme. For something moving exactly at the speed of light, time does not pass. From the photon's perspective, if such a perspective can even be meaningfully defined, emission and absorption are the same instant. This idea is difficult to wrap your mind around, but it reinforces the idea of photons as connectors rather than travelers. They link events across space-time without themselves undergoing a journey. When a star emits light that eventually reaches your eyes, it feels natural to imagine that light traveling for years or centuries, and from your perspective, it does. But for the photon, there is no waiting. There is no aging. There is no in-between. There is only the connection. This is part of why photons are often described as messengers. They carry information about where they came from. The energy they carry tells you something about the processes that produced them. Their direction tells you where that source is. Their polarization can tell you about magnetic fields they encountered along the way. Their arrival time can tell you about distance and motion. Light allows the universe to communicate with itself. Without photons, distant events would be isolated. Stars would burn unseen. Galaxies would evolve in silence. Even within your own body, photons play a role, triggering chemical changes in the retina that allow vision to happen at all. But these messages are not written in words, they are written in structure. A photon's properties encode information, and that information is decoded through interaction. What makes this even stranger is that photons do not carry information in the way a package carries a message. There is no little tag attached to a photon saying where it came from or what it means. The information is implicit in its energy, momentum, and quantum state. This is why light can be analyzed to learn about things unimaginably far away. By splitting light into its component frequencies, scientists can determine the chemical composition of stars. Specific atoms absorb and emit photons at specific energies. Those patterns act like fingerprints. All of that information arrives without anything material making the journey. No piece of the star travels to Earth. Only photons do, and they are not pieces of the star in any ordinary sense. They are the result of interactions that happened there long ago. This again brings us back to the idea that photons are not objects in the traditional sense. They are records of change. Each photon is evidence that something happened somewhere. This perspective also helps explain why photons are the smallest messengers, not in terms of size, but in terms of indivisibility. You cannot have half a photon. You cannot detect a fraction of one. Interactions occur one photon at a time. Even when light seems continuous, like the steady glow of a lamp, it is actually composed of an enormous number of individual photons arriving in rapid succession. The continuity is an illusion created by scale. At human time scales, the discreteness is hidden. At smaller scales, it becomes visible. Sensitive detectors register individual photons as distinct events. The randomness of their arrival times becomes apparent. Patterns emerge only when many events are collected. This randomness is not a flaw or a lack of control. It is a fundamental feature. Photons are emitted and absorbed probabilistically. You can predict averages with extreme accuracy, but you cannot predict exactly when a specific photon will arrive. This probabilistic nature is often uncomfortable. It feels like uncertainty, where certainty should exist. But it is important to recognize that the uncertainty does not lie in the laws. It lies in the outcomes of individual events. The rules governing the probabilities are precise. Photons also exhibit properties that further challenge classical intuition, such as polarization and entanglement. Polarization describes the orientation of the electromagnetic oscillations associated with the photon. This orientation affects how photons interact with materials, whether they pass through certain filters, and how they reflect. Entanglement, on the other hand, describes a situation where two or more photons are linked in such a way that their properties cannot be described independently. Measure one, and you instantly gain information about the other, no matter how far apart they are. This does not mean information is traveling faster than light. It means that the quantum state describing the system is shared. The photons are not separate messengers. They are parts of a single description. This further erodes the idea of photons as independent little particles. They can be correlated in ways that defy classical separation. They can behave as aspects of a larger whole. Even the act of detecting a photon is more complex than it sounds. Detection is not simply a matter of a photon hitting something. It is a quantum interaction that results in a measurable change, such as an electron being excited or a current being produced. Until that interaction happens, the photon is not localized. It is not at a specific point. It exists as a set of probabilities. Detection forces a specific outcome, but it does not reveal a hidden path the photon took. It creates the event. This means that photons are not tiny objects traveling along invisible tracks. They are processes unfolding according to rules that link possibility and actuality. The language of messengers is useful because it emphasizes connection. A photon connects a change in one place to a change in another. It does not linger. It does not leave behind a trail. It simply makes the connection and vanishes. This view also helps explain why photons play such a central role in physics. They mediate electromagnetic interactions. They allow charged particles to influence each other across distance. They are responsible for forces, radiation, and the structure of atoms. In quantum field theory, light is described not as a collection of photons, but as an electromagnetic field that can exchange energy in discrete units. Photons are the excitations of that field. They are the moments when energy moves from the field to matter or vice versa. This framing again shifts the focus away from objects and toward interactions. The field exists everywhere. Photons are events within that field. Thinking this way requires patience. It resists visualization. It does not offer a simple picture you can hold on to, but it does offer consistency. Every experiment fits. Every prediction holds. As you listen to this, photons are arriving from the screen, from the room, from distant lights outside. Each one triggers tiny changes in your eyes. None of them announces itself. None of them leaves a mark. And yet together they build the experience you're having right now. That experience feels continuous, stable, and solid. Beneath it is a constant stream of indivisible events, happening too quickly and too quietly to notice individually. The smallest messengers do not shout. They whisper in numbers large enough to matter. What makes photons especially interesting is that they are both fundamental and limited. They are fundamental in the sense that they cannot be broken down into smaller carriers of light. They are limited in the sense that they only exist as long as the interaction they represent remains incomplete. Once a photon is absorbed, it is gone. The energy it carried has been transferred. The message has been delivered. There is nothing left to examine. This ephemerality is not a weakness. It is part of what allows light to be such an effective messenger. Photons do not clutter the universe. They do not pile up. They appear when needed and disappear when their job is done. This makes light remarkably efficient. Energy and information move without leaving debris. The universe remains clean in a sense, even as it communicates endlessly. Color feels immediate. You do not calculate it. You do not reason your way into it. You open your eyes, and it is simply there, spread across the world in countless variations. Blue sky, green leaves, warm amber light at dusk. The experience is so seamless that it is easy to forget how many steps are involved, how much interpretation is happening, and how little of it actually belongs to light itself. because colour is not something light possesses on its own. It is something that happens between light and you. This is where the idea of colour as a conversation becomes useful. Light speaks in energy. Your eyes listen in biology. Your brain translates. What you experience as colour is the result of that exchange, not a property carried intact from source to surface to sight. To see why this matters, it helps to begin with what light brings to the interaction. Photons arrive with a specific energy. That energy is tied directly to frequency. Higher frequency photons carry more energy. Lower frequency photons carry less. This range of energies spans far beyond what you can see, from radio waves at the low end to gamma rays at the high end. Your visual experience occupies only a narrow slice of that vast spectrum. Within that slice, different energies correspond to what we label as different colours. But those labels are conveniences, not fundamental divisions. There is no sharp boundary where red suddenly becomes orange or green becomes blue. The spectrum is continuous. Colour names are categories imposed by perception and language. When light reaches your eye, it does not arrive as red or blue. It arrives as photons with particular energies. The eye's job is not to recognize colour directly, but to respond differently to different energies. Inside your retina are specialized cells called photoreceptors. There are two main types involved in vision: rods and cones. Rods are highly sensitive to light and allow you to see in low light conditions, but they do not distinguish colour. Cones are less sensitive but come in different varieties, each tuned to respond most strongly to a particular range of photon energies. Most humans have three types of cones. One type responds best to higher energy visible photons, another to medium energies, and another to lower energies. These are often loosely referred to as blue, green, and red cones, but that shorthand can be misleading. Each type responds across a range, not a single point. When photons enter your eye, they interact with molecules inside these cone cells. That interaction triggers a cascade of chemical changes, ultimately producing electrical signals. Different cones respond with different strengths depending on the energy of the incoming photons. Your brain does not receive a label saying this photon was green. It receives a pattern of activity, how strongly each type of cone responded. Colour emerges from the comparison of these responses. This is why colour is a conversation. Light provides the input. Your eye responds selectively. Your brain interprets the pattern. If two different light sources produce the same pattern of cone responses, they will look the same colour to you, even if their actual photon distributions are different. This is not a hypothetical scenario. It happens all the time with artificial lighting. Two lights with very different spectral compositions can appear identical in colour, because they stimulate your cones in the same way. This means that colour is not an absolute property of light. It is relational. It depends on the observer. Different species experience colour differently, because their eyes have different sets of photoreceptors. Some animals see fewer colours than humans. Others see more. Birds, for example, often have additional cone types that allow them to see ultraviolet light. What looks like a uniform surface to you may be richly patterned to them. Even among humans, colour perception varies. Some people have cones that are missing or altered, leading to different experiences of colour. Others have subtle shifts in sensitivity that change how colours appear without ever being noticed. This variability reinforces the idea that colour does not live in the world by itself. It lives in the interaction. Still, light plays an essential role. Without differences in photon energy, there would be nothing for the eye to compare. The conversation requires both participants. The story becomes even more interesting when you consider how objects acquire their colours. A red apple does not contain redness as a substance. It contains molecules arranged in such a way that they absorb certain photon energies and reflect others. When white light, which contains a broad range of visible photon energies, strikes the apple, some photons are absorbed. Their energy is transferred into molecular vibrations or electronic changes. Other photons are reflected. Those reflected photons are what reach your eye. The apple appears red because it reflects photons in the lower energy visible range more efficiently than others. But that redness exists only when there is light to reflect and an eye to receive it. In darkness, the apple has no colour. Under different lighting, its colour can shift. This dependence on context is another sign that colour is not a fixed property. Change the light source, and colours change. Sunlight, candlelight, and LED light all have different spectral compositions. They stimulate your cones differently, altering the conversation. Your brain works constantly to compensate for these changes. This process, called colour constancy, allows you to perceive objects as having relatively stable colours, even under different lighting conditions. A white shirt looks white at noon and at sunset, despite the very different light illuminating it. This compensation is not perfect. Under unusual lighting, colours can look distorted, but most of the time your brain quietly adjusts, maintaining a sense of continuity. That adjustment further distances colour from being a simple property of light. It is an interpretation layered on top of sensory input, informed by experience and expectation. Yet, despite all this complexity, colour feels immediate and effortless. You do not consciously calculate cone responses or spectral distributions. The conversation happens below awareness, producing a smooth result. This smoothness can make it tempting to think of colour as something that light carries intact, like paint on a brush. But the reality is more dynamic. Light offers energy differences. The eye samples them. The brain constructs an experience. This construction process becomes especially clear in cases where colour appears without a corresponding external stimulus. After images, for example, occur when cones become temporarily less responsive after prolonged stimulation. Look at a bright red object for a while, then look away, and you may see a greenish afterimage. The light is not green. The pattern of cone activity is. Similarly, certain optical illusions create colours that are not present in the stimulus at all. The brain fills in information based on context, edges, and expectations. These effects are not bugs. They are features of a system optimized for usefulness rather than accuracy. Colour helps you distinguish objects, assess ripeness, detect changes, and navigate environments. It does not need to be a perfect map of photon energies to be effective. From the perspective of light, none of this matters. Light does not care how it is perceived. It delivers energy according to physical laws and continues on its way or vanishes upon absorption. From the perspective of perception, however, light becomes meaning. It becomes surface, depth, contrast, and emotion. Certain colours feel warm, others feel cool, some feel calming, others feel stimulating. These associations are partly cultural and partly biological. They arise from repeated interactions between light, environment, and experience. Even language reflects this. We speak of bright moods, dark thoughts, warm tones, cold light. These metaphors grow out of how colour and light influence feeling, not just vision. At this point, it becomes clear that asking what colour is made of is as slippery as asking what light is made of. Colour is not made of photons in the same way light is not made of particles. Colour is made of interaction. This does not make it any less real. Experiences are real even when they are constructed. Pain is real. Sound is real. Colour is real. Their reality lies in experience, not in material composition. What makes colour especially interesting in the context of light is how efficiently a small range of physical differences produces such a rich variety of experiences. Tiny differences in photon energy lead to dramatic differences in perception. This sensitivity allows humans to distinguish millions of colours, even though the underlying physical range is narrow. The brain amplifies differences, enhancing contrast and creating boundaries. That amplification can sometimes mislead. Colours can appear different depending on surrounding colours. A grey square can look warm or cool depending on its context. The light itself has not changed. The interpretation has. These effects highlight the conversational nature of colour. The eye does not passively receive information, it actively interprets it. Light, in this sense, is offering possibilities. The eye selects, the brain negotiates. When thinking about what light is made of, colour serves as a reminder that composition alone does not determine experience. The same photons can produce different colours depending on context. The same light can feel harsh or gentle depending on timing, intensity and expectation. This brings us back to the idea of photons as messengers. A messenger does not control how the message is understood. It delivers content. Interpretation happens elsewhere. Photons deliver energy and structure. Colour is the interpretation that follows. As you listen, light continues to arrive at your eyes, triggering countless microscopic interactions. Each one contributes to a seamless visual field that feels stable and obvious. Beneath that stability is constant negotiation. The world you see is not a direct imprint of light on your mind. It is a translation. That translation is usually so reliable that it fades into the background. But when you slow down and consider it, the process becomes quietly remarkable. Something as abstract as electromagnetic energy becomes something as immediate as colour. This transformation does not require awareness. It happens whether you think about it or not. But thinking about it can change how you experience light, even subtly. Colours may begin to feel less like surfaces and more like signals, less like properties and more like conversations that renew themselves moment by moment. Even when you close your eyes, light does not stop. The room may fade from awareness, colours may dissolve into darkness, but light continues to move, to interact, to pass through walls, through air, through your body itself. Most of it never reaches awareness, not because it is absent, but because your senses are selective. What you see is only a thin slice of what is happening. This is where the idea of invisible light becomes important, because it reveals how limited ordinary perception really is. The light you can see, the narrow band of energies that produce colour and brightness, is only a small fraction of what exists. Beyond that thin window stretches an enormous range of electromagnetic activity, filling space constantly, quietly, without announcement. To understand this, it helps to return to the idea of light as electromagnetic radiation. What distinguishes one kind of light from another is not substance, not material composition, but energy, frequency, wavelength. These are different ways of describing the same thing. How rapidly the electromagnetic fields oscillate, how much energy each photon carries. Visible light occupies a modest middle ground. Below it in energy are radio waves, microwaves, and infrared radiation. Above it are ultraviolet light, X-rays and gamma rays. All of these are forms of light. All of them are made of the same kind of messenger, photons. The only difference is how energetic those photons are. This alone can feel counterintuitive. Radio waves and gamma rays feel nothing alike. One carries music into a car, the other is associated with cosmic violence and nuclear reactions, and yet, at the most fundamental level, they differ only by scale, by how tightly their waves are packed, by how much energy each photon delivers. This continuity is one of the most elegant aspects of light. There are no sharp boundaries in nature separating radio from infrared or visible from ultraviolet. Those categories are conveniences created to help humans talk about effects. The electromagnetic spectrum is a smooth gradient. Most of that gradient is invisible to you, but invisible does not mean inactive. Radio waves, for example, pass through you constantly. Signals from broadcast towers, satellites, Wi-Fi routers, and distant astronomical sources move through your body without resistance. They interact weakly with your tissues, carrying information rather than heat or damage. Microwaves occupy a higher energy range. They are still invisible, but they interact more strongly with matter. They can cause molecules, especially water molecules, to rotate and vibrate. This is why microwave ovens work. They excite molecular motion, producing heat. Infrared radiation sits just below visible red light. You cannot see it, but you can feel it as warmth. Every warm object emits infrared light. Your body does. The walls around you do. The Earth itself radiates infrared energy into space. Infrared cameras do not see heat directly. They detect infrared photons and translate them into visible colors. They make the invisible visible by converting one part of the spectrum into another. Above visible light lies ultraviolet. Ultraviolet photons carry more energy than visible ones. They can trigger chemical reactions. They can damage DNA. They can also drive important biological processes such as vitamin D production in skin. X-rays and gamma rays carry even more energy. They penetrate deeply into matter. They pass through soft tissues. They interact strongly with dense materials. They reveal bones. They reveal cosmic events. They reveal processes that cannot be observed in any other way. All of these forms of light are present in the environment to varying degrees. Some are produced naturally. Some are produced artificially. Some arrive from deep space, having travelled for millions or billions of years before passing quietly through you. Most of the time, you are unaware of this constant passage. Your senses are tuned for survival, not completeness. You see what helps you navigate, find food, recognize faces, and avoid danger. The rest is filtered out. This filtering can give the impression that invisible light is somehow separate from visible light, as if it belongs to a different category altogether. But physically, there is no such separation. The same rules apply. The same fields oscillate. The same photons carry energy. The difference lies in interaction. Visible light interacts strongly with the molecules in your retina. Infrared interacts more with thermal motion. Radio waves interact with electrical circuits. X-rays interact with dense matter. Interaction determines relevance. This idea becomes especially clear when you consider that invisible light can be detected and used in ways that extend human perception far beyond its natural limits. Radios convert radio waves into sound. Thermal cameras convert infrared into images. X-ray detectors convert high-energy photons into diagnostic information. In each case, a device acts as an interpreter, standing in for a biological sense that does not exist. The device engages in the conversation instead of your eye, translating the message into a form you can understand. This reinforces the idea that light itself is neutral. It does not come labeled as visible or invisible. Those labels reflect the limits of perception, not the structure of reality. It also reveals how much of the universe operates beyond direct experience. Entire processes unfold in ranges of light you never see. Star formation hidden by dust becomes visible in infrared. Explosive cosmic events reveal themselves in gamma rays. Cold clouds of gas announce their presence through radio emissions. Without invisible light, much of modern science would simply not exist. The universe would appear quieter, simpler, and far less dynamic than it truly is. Even on Earth, invisible light plays a constant role. Infrared radiation governs heat transfer. Ultraviolet light influences weather patterns, ecosystems, and biological rhythms. Radio waves enable communication across continents. These influences do not announce themselves. They blend into the background, shaping conditions rather than demanding attention. This subtlety is part of why invisible light can feel abstract. You cannot point to it directly. You cannot see it without assistance, but its effects are everywhere. Your body absorbs infrared radiation from its surroundings and emits its own. This exchange contributes to thermal balance. The warmth you feel from a nearby person or object is not air alone. It is infrared light traveling between surfaces. At night, when visible light fades, infrared continues unabated. The world does not go quiet. It simply shifts into a different register. This constant presence challenges the idea that darkness is the absence of light. Darkness is the absence of visible light. Invisible light remains. Even deep space, often described as empty and cold, is filled with electromagnetic radiation. A faint background glow permeates the universe, the remnant of its early history. Photons from that time still move through space, stretched and cooled by cosmic expansion, now existing in the microwave range. These ancient photons are invisible to your eyes, but they are real, measurable, and informative. They carry information about the universe when it was young, long before stars or planets existed. This means that light is not only around you in space, it is around you in time. Photons from different eras overlap in the present, arriving together from vastly different origins. Some photons reaching you now left their sources moments ago, others left millions of years ago, others have been travelling since near the beginning of everything. All coexist in the same moment. This layering of histories is easy to miss because perception collapses it into a single experience. The world looks stable, continuous, present. But beneath that stability is a constant flow of messages from different times and places, most of them invisible. The fact that light can be invisible and yet active also helps clarify what light is made of. If light were a substance, invisibility might imply absence. But light is not substance. It is energy structured in specific ways. That energy does not care whether it is seen. It does not require observation to exist or propagate. It moves according to physical laws regardless of attention. This is important when considering ideas about observation and reality. Light does not wait to be noticed. It does not require an eye to complete its journey. Observation affects how light is measured, not whether it exists. Invisible light demonstrates this clearly. It fills space whether or not there is a detector. Its presence can be inferred through effects even when it is not directly measured. For example, the warmth of sunlight on your skin includes a significant infrared component, You feel it even if your eyes are closed. The energy transfer happens independently of vision. Similarly, ultraviolet light can cause sunburn even when it does not feel bright. The damage occurs regardless of awareness. These examples underline a simple point. Light interacts whether or not it is perceived. This interaction-based understanding helps resolve confusion about why different kinds of light matter. It is not about visibility. It is about how energy couples to matter. Visible light couples efficiently to the photoreceptors in your eyes. Infrared couples efficiently to molecular motion. Radio waves couple efficiently to oscillating charges in antennas. X-rays couple efficiently to dense atomic structures. Each range finds its partner. In that sense, invisible light is not hidden. It is simply speaking to different listeners. Your eyes are one listener among many. As you sit quietly now, surrounded by unseen radiation, nothing dramatic is happening. There is no danger implied. Most of the light passing through you is gentle, low energy, harmless. It has always been there. Your body evolved within it.